Hello, in this video we will talk about the first sections of Chapter 5 in bold here, where we discuss quantum numbers. So we begin by talking about the Heisenberg uncertainty principle, and it's formulated thusly that the uncertainty in your knowledge of position, x, times the uncertainty in your knowledge of momentum, which is mass times velocity, is always greater than or equal to Planck's constant divided by 4 pi. And so the delta here means uncertainty in measurement. This is formulated by Heisenberg in 1927. Okay, so to put some pictures on this, if the uncertainty in your position is large, and so this is represented by having a big shadow on our ball here, so uncertainty in position is large, then your uncertainty in momentum, mass times velocity, can be small. There's less shadow here, so you can know its momentum more precisely if you are uncertain about the position. On the flip side, as you know the position more precisely, you wind up knowing the momentum less precisely. Again, this is one of those things that makes sense for small quantized particles where quantum mechanics plays a role. You never see a macroscopic version of this. But okay, so this works for electrons and for other really small particles. So then what does this ultimately tell us? It tells us that the electron cannot orbit the atom on a precisely defined path. We know the velocity of an electron from its kinetic energy, and we can solve for energy in a number of different ways. And we know the mass of an electron very precisely. So since we know its velocity, its mass, that means we know its momentum precisely. It means we cannot know the position of an electron. So these pictures where we draw the electrons as little, planets orbiting the nucleus, or say the electron is on these nice little orbits around the atom, these pictures are 100% false. They look pretty, so they tend to dominate science, but they're not actually correct. So the correct description of how an electron behaves around the atom comes from Schrödinger's wave equation. And so Schrödinger presented an equation in 1926 that describes both the particle and wave-like nature of the electron very well. And so he describes the electron with a wave function. Remember from de Broglie that even though the electron is a particle, it can still have a wave. It still behaves like a wave, so we describe a wave function. So this wave function, it gives you the energy of some electron, and it also gives you the probability of finding this electron in a volume of space. And that's the square of the wave function, gives you that. So again, we can't know the position of an electron precisely, but we can figure out the probability of finding it in a certain position when you square the wave function. Up in the little picture bubble here is the famous equation with a nice little picture of Schrödinger himself. Okay, so some caveats. Schrödinger's equation can only be solved exactly for the hydrogen atom. You have to approximate it for many electron systems, but it still works fairly well. And then I already said the second one, that we can only discuss the probability of finding an electron and don't know actually where it is. Okay, Schrödinger, also famous for a thought experiment about the cat, Schrödinger's cat, that had to do with whether or not a nucleus has decayed and released an alpha particle, which then released a poison which killed the cat. And the cat is both alive and dead until you open the box and look. That actually has nothing really to do with what we're doing here, except for the idea of the probabilistic nature of nuclear processes. Okay, so the Schrödinger equation is just that. It's an equation. You put numbers into it, you get numbers out of it. So this is a scan of my physical chemistry textbook where we're putting numbers into it. Here's 1, 2, 3 numbers that go into it. And we'll talk about these numbers next. These numbers over here are the quantum numbers. So you put the quantum numbers in, and you get an equation out. So here's psi, this is the wave function, and then it's ultimately a complicated function that depends on radius away from the nucleus, which is contained in this sigma term here. And then there's also other directional terms too. There's theta and phi. Math is phrased in polar coordinates, so instead of x, y, z, you have radius and you have effectively latitude and longitude in a way. So irrespective of how complicated the math looks here, Ultimately, you put 3 quantum numbers into an equation, and out of it you get an equation that describes the orbital. So the Schrödinger equation gives you these atomic orbitals, which are where the electrons reside around the atom. And again, this is the wave function, or this is from the wave function of the electron. So we call these orbitals to distinguish them from this idea of an orbit in the Bohr model of the hydrogen atom. So the orbital is the correct physical picture for how an electron resides around the atom. And as we saw when we were doing the Bohr model of the atom, the electrons are jumping in and out of something. It's not actual orbits around the nucleus, it is these orbitals that the electrons jump in and out of when they absorb or emit a photon. So down on the bottom here we have some pretty shapes that show us what these orbitals look like. So how do we draw these shapes? Well, we got to back up a step. The square of a wave function gives you the probability of finding an electron. So in this figure from your book, the thing on the left might be say you found the electron 100 times, where was it? And you drew a dot for each one. Something like that. Right? So you have some probabilistic nature. Okay, mostly you'll find the electron, in this kind of center part, but hey, you might find it farther out as well. And so then, when you're drawing these nice pretty shapes, you just enclose the volume in which you have a 99% chance of finding the electron. This is the 1s orbital, it's spherically symmetric, and we'll talk about that in a few minutes. But that's what we're doing here. We're taking something that's probabilistic and enclosing a shape where you're most likely to find it, so that we have a nice pretty picture that us humans can look at and make sense of. So here we go, let's talk about quantum numbers. So the wave function is a function of really 4 numbers called quantum numbers. I mentioned 3 previously, n, l, ebb sub l, and those are the ones that give you the shape of the orbital, and then m sub s allows you to place 2 electrons into an orbital. And so let's talk about these in turn. So we're going to start with n on the left here. So n is the principal quantum number. It can take values starting at 1 and going up in integer steps, 1, 2, 3, 4. And roughly what this tells us is it tells us the distance of the electron from the nucleus. N equals 1 is closer to the nucleus, n equals 2 is farther away, n equals 3 is farther away. So that's what the principal quantum number gives us. Now, we were using the principal quantum number when we were doing the equations to calculate emission, wavelengths, and frequencies and energies from a hydrogen atom, and also absorption energies through the Rydberg equation. And it turns out for the hydrogen atom with only 1 electron, all the n equals 2 orbitals, for instance, are all the same energy. All the n equals 3 orbitals are all the same energy. So you only need the principal quantum number to make sense out of that phenomenon. However, when you get to other atoms with more than 1 electron, then you start to need the other quantum numbers to give us the other ways the electron can reside around the atom. Okay, so on to the next quantum number. This is the azimuthal quantum number. It's kind of a hard word to say. And we represent it with an L. So this is not a number 1, this is an L here. Now, the azimuthal quantum number for a given value of n, the principal quantum number, L can go from 0 to n minus 1. So, alright, so it's 0 based, starts with 0, whereas the principal quantum number starts with 1. And you can go up to n minus 1. So some examples. So say you have a principal quantum number, n equals 1. Then your values for the azimuthal quantum number L can go from 0 to, well, n minus 1. 1 minus 1 is 0. So you only have one option, 0. Right? Okay. Now if your principal quantum number n equals 2, well then you can go from 0 to 2 minus 1, so 0 to 1. And if n equals 3, you can have 0, 1, or 2 for the azimuthal quantum number. So the possible values that this can take depend on what n is. Now we give letters to these. So if L equals 0, we call it an s orbital. If L equals 1, it's a p orbital. L equals 2 is a d orbital, and L equals 3 is an f orbital. So these letters are historical names, I should say, and they come from atomic spectroscopy and how the lines looked when electrons were transitioning between levels. And so it's the sharp line, the principal line, the diffuse line, and the fundamental line. You don't need to know that. Just know that the origins of the letters are historical and don't really make sense with our modern understanding of the atom. Okay, so roughly, the azimuthal quantum number L gives us the shape of the volume of space that the electron occupies. So again, remember, it's not a true volume. It's, your likelihood of finding it is, above 99% inside some volume. But the same idea holds. So this is the shape. So let me show you some of these shapes. So if L equals 0, well, you have the s orbitals, and the s orbitals are spherical. It just kind of worked out that way that s can stand for spherical in your head, if you want it to. Okay, L equals 1, you get the p orbitals, and these have these little dumbbell shapes. And then there's 3 possible p orbitals, and we'll get into how we know that next. Okay, and then L equals 2, you get d orbitals. It turns out there's 5 possibilities there, and they have these shapes. And then when L equals 3, you have the f orbitals, and there's 7 possibilities, and they have really crazy shapes. I gotta say, my favorite orbital in the whole set is the dz squared. It's got a freaking donut around the middle. How is that not cool, right? And that's just how the math comes out. I should say something about the colors here, is that technically your wave function has a sign associated with it, and you'd have both positive and negative signs in different parts of the atom. When you square it to get probabilities, that doesn't matter anymore. But still, when people draw these shapes, sometimes they'll draw them in different colors to denote that there's different signs of the wave function here. So the source where I got the picture for the f orbitals has different colors to denote different signs of the wave function. And the source where I got the other pictures doesn't have different colors. But if you look at this in some source that has colors, the up and down parts are one color and the little donut's another color, for example. That's a nuance you don't need to know. I just wanted to explain what I have on the slide. Okay, next quantum number in the list is the magnetic quantum number, m sub L. So m sub L can take values depending on the number of L. So if your L, the azimuthal quantum number, is 2, m sub L can go from -2 to +2 in integer steps. And so that's what I have down here on the slide. Where, say, if L is 0, you have an s orbital, m sub L can go from -L to +L, so 0 to 0. If L equals 1, you can go from -1 to +1. If L equals 2, you can go from -2 to +2. If L equals 3, you can go from -3 to +3, so on and so forth. And so this gives you the orientation of the orbital in space. So if you go to these pictures that we were just showing of orbitals, okay, so if L equals 1, your m sub L can take -1, 0, or 1, and this gives you the 3 orientations in space. So these are called p orbitals. You can have a px, a py, and a pz, depending on which Cartesian coordinate axis this orbital lies along. When you go to the d orbitals, well, you have 5 options here for m sub L, which gives you the 5 orientations in space. One of these relates to m sub L -2, one is -1, so on and so forth. Now you don't need to know which orbital comes from which quantum number, but just know that the fact that there are 5 magnetic quantum number values possible for a d orbital tells you that there's 5 possible d orbitals. That's why there's 5 of them. Okay, so to summarize up till now, what are the possible values of these various quantum numbers? Okay, so if your n equals 1, then L can go from 0 to n minus 1, so that's 0. M sub L can go from -L to +L, still 0. We call this orbital the 1s, and there's only one of them. Okay, now if your n equals 2, L can go from 0 to 1. Now if L equals 0, you still only have one of them, and that's called the 2s orbital. All right. If L equals 1, then m sub L can go from -1 to +1, and we call this the 2p. So on and so forth. I'll talk about the n equals 3. Now you can have L equals 2. The azimuthal quantum number can equal 2. and then your magnetic quantum number can go from +2 to -2 in integer steps. And we call these the d orbitals, and this is the 3d. And so when you write this, you write the principal quantum number first, and then you write the letter second. Alright, and then when you have n equals 4, you can have f orbitals, which is what happens when L equals 3. And then you have 7 different possibilities here from -3 to +3. And those are your 4 f orbitals, of which there are 7 of them. Okay, so now we got to get to our last quantum number. So the last quantum number is the spin quantum number, m sub s. And this can take two values always and forever, +1/2 and -1/2. The origin of this quantum number is that electrons behave like tiny magnets. They have angular momentum, which makes us think they're spinning. However, your electrons are not actually spinning. Just they have some properties that makes it look like they're spinning, so we just use the word spin. So okay, if your electron is tiny magnets, your magnets can point two directions. Since it's quantized, those are the only two directions your magnet can point, up or down. And so we'll call up +1/2 just arbitrarily because it sounds good to us, and then we'll call down -1/2. And the ultimate function of this is that it allows us to place two electrons into an orbital. There's a restriction that each electron can only have one set of quantum numbers, and that each set of quantum numbers can only be had by one electron at a time. So if you want to put two electrons per orbital, well then you need to have a quantum number that relates to the orbital that's different than the other electron in that orbital. And you do that by having n, l, m sub l all the same, and then different m sub s values, which would then allow you to put two electrons into an orbital. Okay, so now we get to the summary. The existence and energy of an electron in an atom is described by its unique wave function. So unique because each electron has a wave function with one set of 4 quantum numbers, and it's the only one that can have that, the only electron that can have that at a given time. Now, this wave function depends on these 4 quantum numbers. N is the principal quantum number. It roughly tells you the distance from the nucleus, and it can take values starting from 1 and going up in integer steps. The azimuthal quantum number can go from 0 to n-1, and that tells you roughly the shape of the orbital. And then we call these with letters. 0 is S, 1 is P, 2 is D, 3 is F. Alright, so then depending on what L is, m sub L, the magnetic quantum number, goes from -L to +L. And this roughly tells you the orientation of the orbital in space. And then between -L and +L, they're integer steps. So you could go from -3, -2, -1, 0, 1, 2, 3. Okay, and then m sub S, the spin quantum number, is always +1/2 or -1/2, and that allows us to put two electrons in a given orbital. Now we'll talk about this more in the next video, but the Pauli exclusion principle tells us that no two electrons in an atom can have the same set of 4 quantum numbers. Okay, which I think we've talked about already. Cool. Here's another summary, right? The first 3 of these quantum numbers give you the orbital, and then the m sub s value allows you to put 2 electrons into that orbital. Alright, here's another summary that you can look at. If this one makes more sense to you, it tells you the kind of possible outcomes for n equals 1, n equals 2, and n equals 3. And then within each one of these orbitals, so say this one right here, it can fit 2 electrons in there. So in total you can put 2, 4, 6, 8, 10 electrons in the set of d orbitals. Because there's 5 d orbitals, each one can hold 10 electrons. And so on and so forth. Okay, so we have some example problems now. So first problem, which orbital could be represented by the quantum numbers n equals 3, l equals 1, and m sub l equals -1? Pause the video, think about it, and then I'll come back with the answer in just a second. Okay, to do this problem, it helps to just step through the quantum numbers in order. So starting with n equals 3. Alright, so n equals 3 tells us principal quantum number is 3. And when we write these orbital designations, we'll write the principal quantum number first. So if n equals 3, that means our answer is going to have a 3 in the front. So that means we can cross off the 1, and the 2. So that only leaves us with two options. Great. Now, L equals 1. So remember, if L equals 0, that's an s orbital. If L equals 1, that's a p orbital. If L equals 2, that's a d orbital. And if L equals 3, that's an f orbital. So looking at this, L equals 1, that means we have p. So we can cross off the 3s. And then this tells us that our answer is E, the 3p orbital. Now, m sub L negative 1, it tells us that there's going to be 3p orbitals. Your options are negative 1, 0, or plus 1. We don't know which one relates to x, y, and z. I mean, scientists know. That's not something I need you to know. So that part doesn't matter. I put 3py on here. Great, right? You know it's 3p, and that's enough to answer the problem. Okay, another practice problem. This time, answer it for the pop-up question that's going to come up, and we'll go from there. Okay, I'm going to explain the answer because I already have the PowerPoint slide made. Why not? So how many 2p orbitals are in an atom? Well, if you look at 2p, n equals 2, okay, because there's a 2 in front, and L equals 1 because we wrote the letter p. So now when L equals 1, then m sub L can go from negative 1 to plus 1 with three possibilities, negative 1, 0, plus 1. Each one of these magnetic quantum numbers gives us a description of an individual orbital. Since there's three of these quantum numbers that are possible, it means that we have three orbitals. So there's px, py, and pz. Alright, last question. How many electrons can be placed in the 1s subshell? Think about it for a second. 1s, n equals 1. S means there's only one orbital there. So L equals 0, m sub L equals 0. We only have one possible orbital. It can hold 2 electrons. So one thing we can do is we can write that there's two allowed sets of quantum numbers here. You have 1, 0, 0 plus 1/2 and 1, 0, 0 minus 1/2. And this is helpful because it introduces you to this idea that we'll often write sets of quantum numbers in this fashion, with parentheses, commas in between each numbers, and in order. Principal, azimuthal, magnetic, and spin quantum number, in that order. Now, another thing we need to talk about is that sometimes we draw arrows on lines to represent electrons in orbitals. So you can draw a line for the 1s orbital, and then you can draw arrows up here to represent the electron in this orbital. So kind of by convention, we start by drawing the up arrow first and say that's plus 1/2. Then you can also draw an upside down arrow, or a down arrow, and say that represents minus 1/2. So in this 1s orbital, it can hold 2 electrons with different spin quantum numbers, and we can draw them like this. So if you were going to put electrons in the 2p subshell, you would have 3 lines, because as we saw in the last problem, there's 3 different p orbitals that you can use, so you'd have 3 lines, and you could put 6 electrons in there. Okay, I'm going to conclude by showing some pretty pictures of orbitals because I think these things look awesome. And so this picture, okay, I had the s orbitals here. So the 1s is a sphere. Now 2s, from the outside, it looks like it's also a sphere, and the same with the 3s. But they're actually nested shapes. It's like a sphere within a sphere within a sphere for the 3s. And over here on the left we have radius on the x-axis, so radius away from the nucleus. And then on the y-axis we have a distribution function, which what that means is it tells you the probability of finding the electron here. So when you're high up on here, that means you have a high probability of finding the electron this far from the nucleus. Okay, but what's interesting on here is if you look at the 3s, there's a small probability of finding the electron close to the nucleus that overlaps with the 1s. There's a small probability of finding the electron here, which overlaps with the 2s a little bit. Then there's a node, and there's a node here too. There's 2 nodes, which basically mean no probability of finding the electron. And then you have the biggest chunk for the 3s, right, where you're most likely going to find the electron. But ultimately, these are like Russian nesting doll orbitals. So to expand on this idea of a nodal plane, or of a node, right, a node is a place where there's no probability of finding the electron. So when you look at the p orbitals, there you have these three different orientations, x, y, and z, and in between the two lobes of the orbital, there's an area where you have no probability of finding the electron, which we call a nodal plane. Another word I want to introduce is how we use degenerate in chemistry. It's much different than how you use degenerate in your everyday life. And here it means having the same energy. So px, py, and pz, all those orbitals have the same energy. So electrons can hop between orbitals without emitting or absorbing any energy. And we say that these three p orbitals are degenerate. Okay, here's the d orbitals. There's many nodal planes here. And again, this slide and the last slide, the different signs of the wave function are colored in different colors, and that's something we don't need to know at the moment. I just want to point out why we have different colors. And again, all orbitals are the same energy here, they're all degenerate. A caveat here is, except when you have inorganic transition metal complexes, coordination complexes they're called, we talk about this in the end of the second semester of Gen Chem, and you get some interesting outcomes when these orbitals are no longer degenerate. Okay, here's the f orbitals. They look cool. There's lots of nodal planes here that you can see. Alright, and then I really like this picture because it shows you what all the shapes look like beyond just the first one, right? You know, most times you'll just see, oh yeah, here's the S, here's the P, yep, here's what the D looks like. But it doesn't show you that as you go to higher and higher principal quantum number values, you get these really weird nested shapes. I just think it looks cool. Okay, last slide. Why are atoms spherical? Experimentally, atoms appear to be very spherical, but we have all these orbitals that are not spherical. And it's because when you look at the overall shape of the atom and all the orbitals around it, it does tend to kind of average to a sphere. And so you can approximate atoms as spherical, and it's a pretty good approximation. Okay, thanks for hanging in there with a really long video. We needed to talk all about quantum numbers, and now we have. Cool. So remember to watch all the way to the end to get credit for answering the question, and thank you very much for your attention. I knew it was a long one.